Good morning, good evening, wherever you may be in your day. I thank you as always for making chemistry part of that day. Okay, so ends gas laws with this video. So almost all these concepts we've talked about, but I want to formalize it. The theory behind what we've been talking about is called the kinetic molecular theory of gases. So gases take up no space or volume essentially. They move in straight lines until they hit something, and then they bounce off it, and they move in another straight line until they hit something. There's no stickiness or forces of attraction. When they collide, the energy is conserved. They're elastic collisions, so think like pool balls hitting each other. And the average kinetic energy is proportional to temperature. And I've always said temperature is kinetic energy. So nothing really groundbreaking here. And then we want to talk about the particles, and this is kind of what I wanted to get at, was if we want to say what happens to the pressure when we decrease the volume, how do we explain that in terms of kinetic molecular theory of gases? Well, again, pressure is due to the force from atoms striking the outside of the container. So if we make the container smaller, there's going to be more collisions with the outside of the container because they're closer to the outside at all times. So more collisions are going to increase the pressure. If we look at 2, what happens if we increase the temperature? If we increase the temperature, they move faster, so when they hit with more force, and they're moving faster, so they get to the outside more often. So both of those are going to increase the pressure. If we have more gas molecules there's going to be more collisions, and that'll increase the pressure. And lastly, if we go from hydrogen to nitrogen, it's not going to change the collisions. So that's going to have no effect on the pressure. So that kind of general explanation of what's going on. I think that's pretty straightforward. And again, I've been trying to sprinkle this idea throughout all the videos on gas laws. This is a little bit different, and mainly it's a unit issue. But if we want the average speed of a gas, so V is for velocity, it's equal to the square root of 3 times the ideal gas constant times temperature divided by the formula weight. There's some odd unit things going on. I'm not going to derive where this unit's coming from. But we want to use the other version of R, the one that's joules per mole Kelvin. So it's going to be 8.314 joules per mole Kelvin, still a constant. Just look it up. You don't have to memorize it. Just realize we need the energy one for speed. And then because of this, inside the joule, that's a combined unit, is a kilogram. So we actually have to do our formula weight in kilograms. So what would that look like if we want to calculate the average speed of nitrogen at 20 degrees Celsius? 3 is 3. R is still a number we look up, but at this time it's 8.314. Our temperature still needs to be Kelvin. And then our formula weight, instead of being 28.02 grams per mole, we need to convert that over to kilograms. So this would be 0.02802 kilograms, and the average speed then comes out to 511 meters per second. So 2 things here. That's fast. That's over a quarter mile per second. 400 meters is a quarter mile. So that's like a third of a mile in a second. So these gas powered particles are moving fast. That's not even all that warm a room. Your room right now might be warmer than that, in which case it's going even faster. And then the second thing is, if we wrote this twice and divided and simplified, and I'll cut out the math, the magics, you'd end up with this expression, that the ratio of the velocities is the inverse of the square root of the ratio of the formula weights. So we want to take hydrogen versus nitrogen, and we want to know how much faster is hydrogen to nitrogen. We can do that. Formula weight of nitrogen is 28. Formula weight of hydrogen is 4. We take that square root, and we get 3.7 times faster. So, again, it's a ratio, it's a square root. I cherry-picked with hydrogen, so we get a fairly large difference. If you did oxygen and nitrogen, you'd see this ratio would be much smaller. So how can we use this kind of idea of ratios, of speeds, and what affects speeds? Let's get into effect, and there's really only 2 things to talk about. One is temperature. I think you probably already know the answer here, but if you increase the temperature, you increase the speed. And then we want to talk about formula weight, we just looked at that, and if you decrease the formula weight, you're going to increase the speed. So we want high temperature, small formula weight, that's going to maximize our speed. So both of these graphs have speed on the x-axis and number of molecules on the y-axis, and they're looking at the different ideas. What I want to point out is, if we were kind of in calculus class, the area under the curve for both of these would be the same. We're looking at the same sample of gas. But if we increase the temperature, you can see where that peak or average temperature, average speed with each temperature, so that average point for each is going to move farther out. So higher temperatures have faster speeds. And lastly, I'd also like to look at the distribution. So if we look, the faster something's moving, the greater distribution there are of those gas molecules. So how do we see this? We see where the peak is lower. The peak is lower because there's more different values being stretched out. So it's more variable, more entropic, if you want to go back to that idea. And then if we look at speed, same idea. Same number of molecules, so the area under the curves are the same, and what we're seeing is oxygen at 32, 28, 18, 4. We're seeing that average speed increase as we decrease the formula weight. So those are the two things I want to get out there. Oh, actually 3 things. One, all of them are not moving at the same speed. There's a distribution of speeds. The greater something's moving, the greater that distribution. Things at higher temperature move faster, and things that are lighter move faster. And lastly, they move fastly in and of themselves and just moving and spreading out. That's called diffusion, from high to low concentration. And effusion is high to low pressure through a small gap. So we could fill a balloon with, say, nitrogen and hydrogen, equal parts. And then if I take a little needle and I put a little hole in my balloon, what am I going to see happen? Well, we just did this calculation, right, where hydrogen moves 4 times faster. So we're literally going to see more of the hydrogen go out of the balloon with the nitrogen. Now, I would like to point out 2 things. This is not every hydrogen goes through and then nitrogen's done holding the door for hydrogen and then nitrogen goes through. They're both going through the hole. It's just randomly when those molecules get there and hit that opening and go through. The faster they move, the more likely they are to hit the sides, the more likely they are to hit that open spot, and statistically speaking, they just pass through faster. So hydrogen's going to get out maybe 4 times faster, 3 times faster, and this question can be worded a couple different ways. If we're looking at this rate of diffusion, it's the same thing as your speed. So if hydrogen is 3.7 times faster, it's going to fuse 3.7 times faster. It's also going to diffuse 3.7 times faster. So these words in some ways are interchangeable. Hydrogen is going to be much faster than nitrogen. And what we're going to see then is if we're looking at what's left in the balloon, sometimes I've asked this as a question on a test and service people. What's left in the balloon is going to be less of both. The pressure for both is lower than before there was a hole in the balloon. But the pressure of nitrogen is now going to be greater than the pressure of hydrogen, since hydrogen fuses faster due to a lower molecular weight. So those are all the concepts in one sentence or explanation. And that's pretty much it for gas laws. Sorry to do all these gas law videos at night. I know I'm probably looking tired at this point. And I promise next week I'll be back to morning taping. Had a few conflicts this week. And yeah, that's about it. So hope you enjoyed gas laws, and we will be back to bonding and bonding motifs with our next unit.